Well, hi, everybody, and thank you. That actually is a field promotion for me. I'm not a chief data scientist. I am a special consultant and contributor to VentureBeat. So the chief data scientist is here. So thank you all very much for joining us through lunchtime. This is the dedicated group. These are the groups I like to see, people who really want to be here. So thank you. We're going to spend just a couple of minutes here and get you out to lunch in a few minutes. So how many people here are gamers or follow gaming? So if you are, you probably know that the newest badassest gamers around for things like Quake 3, Montezuma's Revenge, Dota 2, and a bunch of other games are not players at all. They're reinforcement learning. Now, if you're a game person, you may have heard that term. You may have seen it bandied around. We're starting to see some commercialization of it by people like Uber, DeepMind, OpenAI, to take what has been successful and produced killer players in gaming and take it over to larger enterprises, to be able to take the technology and the knowledge and transplant it and move it out and leverage it for bunches of different businesses, from warehousing to, I've got a whole list here. I won't read you the whole list. We'll hear about them. But there are new applications in almost every industry now. So we're going to talk for the next couple of minutes about what is reinforcement learning. And some of you might have a basic idea. For those of you who do, this will be a little bit of a refresher. For those of you who don't, we'll give you a quick level set about that. What it can do, why it's different from machine learning, why enterprises are adopting it, some of the kind of benefits that can come from that, a little bit about what it takes to do it from a hands-on kind of infrastructure way, and then some pros and cons about it. And the format we're going to do today is a short presentation by GP, and then we'll get him back to the couch here and do maybe about 10 minutes of Q&A. We're small enough here that I think we could probably take your questions too. And if we don't get to them in the session, I'm going to volunteer you to be late to lunch, and you can hang out and engage him here or elsewhere. So good brisk session. GP, thank you very much. As announced, he is the chief data scientist for Accenture. He's on the cutting edge for Accenture on this, and is going to give us a quick flyover view about what it is and what it does. So GP, welcome again.
Hi, good afternoon. Welcome, everybody. This is GP. I'm from Accenture. I work as a chief data scientist for them. And today we're going to see the promising landscape of deep reinforcement learning. And also we're going to see how it basically evolved from so many trends of machine learning. So if we take a look at machine learning has been there from 1950s, and then it started trending in 1980s with different types of mechanism, and then it really shot to fame in 2000s with Bayesian networks, neural networks, and bio-inspired algorithms and evolutionary algorithms, and a bunch of other algorithms for genomics, healthcare, and different types of techniques. So in the supervised machine learning, basically what happens is it's going to be taken as input and output pairs like X, Y, based on the labels. And the most prominent techniques we apply is usually classification and regression algorithms. And then we predict the outcomes of the data. So it tries to find the patterns in the data, and it produces the outcome with a specific prediction of how the data is going to look like in the future. It could be financial industry, or it could be healthcare, where we're trying to find the deterioration of a cell and then project and understand how it's going to be like in the future. So various fields have been applying machine learning successfully, but the key for the machine learning with supervised or unsupervised learning is actually the data. You need massive amounts of data that you can feed to the machine, and it can basically process it. And from the pile of data, automatically it derives the outcomes and predictions based on different algorithms. But now, moving away from the classical supervised and unsupervised machine learning, if we are going towards the AGI, because the reinforcement learning is expected to take us to the next level of artificial intelligence, which is the AGI, the artificial general intelligence, where so many companies are trying to power the machines with consciousness, because It is not about data or labels anymore. It's about the tuples of, for example, we talk about SAP and R and delta. So basically, it is operating on an infinite horizon and tries to provide you the finite space, which is S, and then the specific action that the machine learning needs to take through reinforcement learning, which is A. And then there is a transition function that happens with P, and there is a reward for every specific action. And based on the reward, and there's also cumulative discount factors that it gathers. So basically, that means the past has not much of a relevance in terms of historical data sets. So if you're taking a look at chess, for example, it has to make dynamic moves. It's not something like, or if you take any UAV or any vehicle operating either on the Earth or on the space, it doesn't have the prior knowledge of this specific environment of the landscape, how it's going to operate. So it has to learn that on the fly and understand it and take specific actions. And with each specific action, it learns from the data and from the live environment, and then it basically navigates on its own without any historical data sets. So that's the fundamental difference between the machine learning and reinforcement learning. So here, let's take a look at the earlier successes of AI, where AI has been making a lot of trends in the history, and see how reinforcement learning has been shot to fame. So in 1950s, artificial intelligence began with just some type of a rule-based system. And then eventually, if we look at 1980s, most of the systems were feeding the machines with knowledge-based data. It's basically like your knowledge-based data. That means like you are encoding the machine with millions of rules to perform specific action. Okay, if A is B, do this. If B is C, do that. So that's, you have so many rules. It's not like you have some type of intelligence built in the system that it can perform on the fly type of dynamic decisions. But that actually has slowed down the efforts of artificial intelligence. And then because we are trying to create the common sense in the machines just by powering it through the rules. So then that's when the whole shift has begun in the artificial intelligence. And in early 2000s, the world has slowly started shifting towards the reinforcement learning. And the reinforcement learning is where we have a completely different trend. The reason being that as early as in 2012, we have neural networks that operate several companies with deep learning. And deep learning is the second trend in the history of AI, the first trend being the machine learning. Because you're not only able to power the machines with neural networks, you're able to power them through deep neural networks. That's deep learning. And that's when the final shift has begun in AI with the reinforcement learning. So that's the third and final shift in the artificial intelligence. So we are now able to move away from the labeled data and power the machines just with dynamic actions and rewards. And if we take a look at some of the groundbreaking, revolutionary achievements that humans have accomplished with, for example, if you take like DeepMind. DeepMind has AlphaGo. AlphaGo basically runs through the special search Monte Carlo algorithm, and it performs it so well that it calculates the success probability rate more than 90% before it starts making a move. Because the human, when you are playing chess, you only have so many options and probabilities, but it can calculate incredible amount of probabilities. And it succeeds, and it has succeeded with 99.8% success rate, and it has beaten all the human champions on AlphaGo, the Go players. And if we take a look at so many practical applications of reinforcement learning, there is, and let's take a look at the state of reinforcement learning adoption in the enterprise. What several companies are already doing, how this AI has been integrated into the lives of businesses, like daily lives. So if you take a look at healthcare, like if you're looking at cure for cancer, or you're looking for chemotherapy, clinical trials, there are a lot of applications that have been built on reinforcement learning. And for example, for sepsis treatment, or cancer treatment, or if you take a look at chemotherapy, all of these have been powered by the reinforcement learning. And they're so individualized treatments for each person. It doesn't have to be a general reinforcement learning algorithm. It's so specialized for each healthcare need. And looking at the other aspects of the industry, like if you want to build smart factories where the robotics that have been creating revolution in terms of industrial automation, or if you're looking at several other manufacturing, supply chain management, retail, any other industry, they're all powered by reinforcement learning. And so there are so many applications and different types of reinforcement learning algorithms that can actually be applied into text mining. So basically, you want to generate the text, or you want to predict what the text is going to look like based on the current text. Reinforcement learning can do that. And so some companies already have been successful in applying this, in doing this. And it can also read the summaries of text automatically through reinforcement learning. And here we can take a look at how this DeepMind's AlphaGo pipeline of neural network architecture looks like. And so this is basically taking the policy network, and it's evaluating the rewards, and it counts the cumulative factor. It just takes the Monte Carlo algorithm and performs all the possible millions of moves in a fraction of a second. And then it just takes the most successful and probabilistic move to compete against the human players. So also, if we take a look at finance, IBM has implemented a specific reinforcement learning application for stock trading. And that is built on the IBM DSX platform on IBM Watson Studio. And basically, there's an offline training that occurs on it. And once it gets all the information, then it's going to take the day-to-day stocks, and then it predicts the outcomes for how the stock is going to look like at the end of the day. And that's what it is a practical application. It's already working. And again, JP Morgan also has implemented a number of algorithms for the trade execution with reinforcement learning algorithms. And so it's not just restricted to games anymore. It's in every walk of life, in every industrial application. It could be e-commerce, it could be retail, it could be manufacturing, semiconductor, life sciences, healthcare, you name it. Any application has wide implications of reinforcement learning. And there are already production live deployments of these applications from reinforcement learning. So let's take a look at the building blocks of reinforcement learning, how any business can leverage the reinforcement learning, and how it can implement for their organizations. So basically, here if you can see the popularity of programming languages, and every organization has their own set of programming languages, frameworks, tools that they would like to leverage. And the reinforcement learning can actually be implemented through a number of such frameworks. Like it could be implemented in TensorFlow, or it could be implemented with Scikit Python, or it could be implemented through PyTorch or Keras, Jupyter Lab. Again, people may have different type of high-performance computing, cloud computing platforms on their businesses. Maybe they're running Google Cloud, or they're running Azure, or it could be AWS, or SAP Cloud Platform. Any cloud platform, you have a specific framework that you can take it and deploy it and build the enterprise application and just roll it out for the customers. So, because previously there were only few applications that were available for reinforcement learning, like Python being the most popular framework, but in the recent times, we also have PyTorch, and that has been revolutionizing the reinforcement learning, which has actually been utilized to build mobile applications for Android, iOS, and you also have a number of web frameworks or streaming framework platforms that can utilize any data, like if you have electric grid data that is transmitting the data into smart meters, you could utilize that and predict your future outcomes with reinforcement learning. That can be implemented with such frameworks. And also you have a number of other frameworks that you can utilize for building applications for the enterprises. So now let's take a look at another challenging problem here, which is building smart cities. So in order to build smart cities, we need to leverage the existing infrastructure in the most efficient way. It's not always about building new infrastructure, but it's about optimizing the existing infrastructure and trying to build. So basically, MIT has built this deep traffic, which is an application, and to solve the problem of the traffic. So the way that it has been done is basically this entire algorithm has been crowdsourced. So basically, when they have outsourced it, they have received around 24,000 entries from different reinforcement learning researchers, and they have built this algorithm leveraging the off-policy reinforcement learning, and it has generated 96.6 years of reinforcement learning simulations. So basically, that means that whenever there is a traffic, it's always a possibility that there is a way out from it. The traffic is not operating efficiently to get around on the multi-lane freeway. So these specific algorithms have shown how this can be implemented and solve this problem. I mean, normally, if you were to find a way, you will have few solutions to beat the traffic. But if you're taking reinforcement learning, it gives you 96.6 years of simulation. That means like you have so many ways of solving the traffic problem. It's the same problem, but multiple solutions. And also, like, it has basically the concept has been taken from several other gaming environments, for Mujoko environment, Atari, all of these gaming environments, arcade learning environment. They have been applying these machine learning algorithms, and they have been applying it to the practical applications of real world, where, for example, like deep traffic is solving the real world problem, where we are trying to make the infrastructure and smart cities just by finding the efficient paths in the traffic. So what are the advantages and disadvantages of reinforcement learning? So the advantages is that you necessarily don't need to have some massive amount of historical data sets to make a decision. And when we go to machine learning with supervised and unsupervised learning, you will need to have a number of inputs and outputs with labeled data to come to that type of prediction. But the reinforcement learning does not require so much of data. And there might be still some offline training for the algorithm with some offline data, but that does not necessarily mean that it's going to, for example, like robotic arm gating or stuff like that. It does not require so much of data. It just learns it on the fly. And that's where the reinforcement learning can be applied with. It's based on the mathematical foundations of Markov decision processes with a combination of the states and actions. And finally, it predicts the specific action rather than specific prediction of outcome. And that is where it is gearing towards the AGI. And Well, it can only, the disadvantages of reinforcement learning is it just is within the definition of the behavior defined for that algorithm to function. So we're going to define the criteria, and that's exactly what it's going to do. It's not going to do any actions beyond what it has been set in the definition. So that's the disadvantage. And if we take a look at human brain, we have 87 billion neurons. And these neurons connect with synapses and emit the chemical signals and transmit the data from one point to another. But finally, it emerges with a single decision. So that's what reinforcement learning is trying to do, is basically build so many deep neural networks that it can make dynamic decisions and power the machines with that. And if we can do that, actually you can power the machines with common sense, way different from what we were used to do before with encoding with millions of rules and then programming with all the rule-based and knowledge-based systems versus a dynamic, evolving system that can make a dynamic decision at runtime. And that's the complete advantage of a reinforcement learning for any application in an industry. So if we take a look at the recommendations in terms of what reinforcement learning can do, or what is the scope of future research, what is the scope of the applications where the industries can leverage and apply and build practical applications. So for example, like if we take a look at LiDAR, light detection range technique, similar to radar, which does the audio range detection technique. And LiDAR is basically a sensor that can be put in any car. And whenever it navigates through different environments, it just picks up the objects on the fly, and it makes a decision whether it needs to make a left turn, whether it needs to make a right turn. And this is not just for the Earth, but it can be applied for space exploration. NASA has been applying these reinforcement learning algorithms to launch different types of spacecrafts so that whenever they go to different types of planets, it could be in the part of the solar system or it could be exoplanets, but wherever they're sending it, basically they don't have a prior understanding of that environment, how the whole surface looks like or the navigation of that planet looks like. But still, it can on the fly pick up the navigation, and it can detect through the LiDAR sensors, and it can navigate through such complex environments. And it doesn't have to be specific to Earth. It could be applied to any environment. And that's where the future of reinforcement learning is going to be, where people can apply it to different types of industries, including the space industry.
GP, thank you.
Thank you.
Appreciate that. We're running pretty close to the end of time here, so a couple of quick questions. And again, GP will take some questions here if people want to hang out afterwards to ask him. So what, a good overview. So could you just characterize, you've already done it, but just to roll it up at a very high level, what are the characteristics that people who might be out here from enterprises ought to be looking at about what makes a good application and a use case for reinforcement versus conventional machine learning? You've described it, but if you were to just, in a nutshell, give them a way to talk to their management peers about it, what's a good use case for that?
So basically, it depends on the type of industry. Like if people are already building a lot of applications on the e-commerce side, for example, they would like to predict the customers' trends, or they would like to predict the outcome. Like eBay has already done that for auctions, for example. Like they just understand the customer preferences on a dynamic environment. It's not from an historical data set, just at that particular season or even that particular day. It can predict that, and it can basically come up with some type of a specific outcome saying, okay, here are the recommended products that it can be applied. Because Amazon has implemented this recommendation system with regular machine learning algorithms. But eBay has actually taken it to the next level, applying through reinforcement learning, which is because these are all season products. They're not like Amazon runs the products differently and eBay does differently. So for most of this type of season products, reinforcement learning is the best algorithm suited for that type of industry. And it depends on the industry again. Like maybe if you are in aerospace industry, reinforcement learning can be applied differently. And it can predict the meteorological outcomes of the events, just picking up the climate on the fly from the sensors, and it can predict what is the meteorological climate is going to look like in the next few hours. And that is really helpful because instead of relying on a satellite data, it can pick up the live environment and understand the trends and make some decisions in terms of like it needs to be rerouted or it has to stay course, or different outcomes can be predicted from such things. Because other companies like Boeing and Airbus have implemented like attaching thousands of sensors on their wings, and they're just picking up the climate data on the fly, and they're trying to predict the actions for the forecasting the weather. But reinforcement learning, it doesn't require all of that. It can just pick up the data on the fly, and it can make a decision, which reduces a lot of complexity of manufacturing so many sensors and embedding them into wings. This can be avoided. And also, it doesn't require like a post-analysis of if something goes, a plane crashes. People want to understand what went wrong with the plane. It can tell on the fly, this is the reason why things are going this way. It doesn't require like a post-analysis.
Great.
So those type of applications can be achieved.
Excellent. GP, thank you. We're actually going to have to wrap here because we're bumping into lunch and we've got to keep our priorities straight. So thank you. A terrific overview. I know Accenture has a lot more to say about that, and you do too. So if you'd like to find out a little bit more, GP will hang out here for a few more minutes. And otherwise, I want to say thank you, and then we'll hear some lunch details. So appreciate it.